Good morning, calculus class today. So I want to talk about the part one of FTC, Fundamental Theorem of Calculus, and part two. Okay, so we'll take a look at that. For this one is section 5.3. Again, we're not doing 5.1, 5.2, the Riemann sum. So we'll skip through those sections. For calculus AB, so let's say next year. So for those senior taking that in college, you're going to be seeing those stuff again. So now take a look at that 5.3 Fundamental Theorem of Calculus. So part 1 of FTC. So this one is showing that the conditional statement. If f, the function is continuous on the closed interval from a to b, then the function g defined by g of x equals the integral from a to x. So you see the sign like this. It's called the integral f of t dt. And x is right between a and b. So it's bounded right between a and b. So it's continuous on the closed interval AB and differentiables on the open interval AB. So and g prime of x is just the same as f of x. Again, anytime they see that the sign like this, it's called the integral. So integral, that means you want to find the area under the curve. Okay, so let's say that f of t is the derivative, and then once you integrate it, so you get back to the original functions. So let's say that f of t, it's just the velocity. Once you integrate it, you'll get the position function. Okay, so now to look at that, the other part right here. So using part 1 of FTC to find the derivative of the function. So for this one, so instead of integrating it, so we just want to take the derivative on both sides. Okay, so we'll look at that in a minute. Okay, so for A, so let me just write it down here so I need more space. Okay, so for A, so we do have g of x, so that equals the integral from 1 to x of 1 over t to the power of 3 plus 1 dt. So taking the derivative, that means we take d over dx on both sides. So d over dx on both sides. So once you take the derivative, and then you'll see that the integral signs all happening at the same time. So basically that the integral sign and the derivative symbol, so that just got canceled. So this one turns out to be g prime of x. So once this one got canceled, so basically we just have the original integrand remain. So the original function here, so the derivative itself, it's called the integrand. So integrand, so the original variable, that's t. But now we need to replace that t by x. So we need to change that variable. So we got 1 over x squared plus 1. Okay? So that turns out to be the original derivative. And now don't forget about this. So we need to apply the chain rule for this. So derivative of x, which is considered 1, and then derivative of 1, so that's just 0, so there's no need to worry about that zeros. So multiply by 1, so that means g prime of x is 1 over x squared plus 1 for g prime of x. Okay? So now let's try the next one and see what happened. So taking the derivative both sides. So taking the derivative on both sides. So this one turns out to be g prime of r. Again, derivative of the integral, this one just got canceled. So, and this one, again, the original element, this one is the original integrand. So now we need to change the variable. Instead of using x, we're using r. So it's going to be the same as square root of the quantity. So it's r squared plus 4. And then times derivative of r, which is 1. Okay, derivative of 0, that's nothing. So derivative of r, which is 1. So that means multiply this. It's just the same thing itself. So this one is quite simple. Okay, it's not that difficult. Okay, so now what about this type of problem here? So this one I need to set up the new slide. So, and for C, we do have capital G of x. So that equals integral from x to 1 cosine of root t dt. Okay, so for the rest of this, let me just copy it down on a piece of paper, and then I'm going to transfer that to the new slide here. Okay, we'll deal with that in just a minute. Okay, so for E. Okay, so now let's take a look at that for the rest of the example here. So I need a new slide file. Here we go. Okay, so now for C. So for C, we do have g of x. So that equals the integral from x to 1. And integrand, it's cosine of root t dt. Okay, so now one thing that you need to do. So normally, according to FTC part 1, so the line up here, it's got to be integral from a constant to a variable. So what we need to do here, we need to flip this one over. So that means g of x turns out to be integral from 1 to x. Now, anytime that you want to flip the boundary over, so that means you want to change the sign of the integrand. So instead of being positive, so this one turns out to be negative. So once you flip this one over, once you flip that a and the variable over, so that means you want to change the sign for the integrand. Okay, so that's just one of the rules. And now the next step that you want to do, so let's do some analysis. So again, so this one is g of x. So taking the derivative both sides, so taking the derivative with respect to x. So this one turns out to be g prime of x. And then the rest of this, again, replacement, instead of using t, we're using x. So it's going to be negative cosine of root x. And derivative of x, which is 1. So multiplied by the original function, so it's the same thing. And derivative of 1, that's 0, so there's no need to worry about it. And that's it. So g prime of x. Okay, so now let's see what about the next problem here. So for D, we do have y equals integral from 1 to cosine of x. And integrand, it's 1 plus v squared quantity to the power of 10. And then dv. Okay, so one thing that you want to do, make sure that it's a constant to the variable power. Now, gotta be careful, the variable here, it's not just a variable, it's a function. It's a brand new function. So we'll deal with that later. So again, taking the derivative both sides, so d over dx. Okay, so d over dx both sides. Okay, so now, as you can see that, this one turns out to be y prime. D over dx with the integral, so it just got canceled. And then derivative of the original integrand, so we just want to replace that v by using cosine of x. So we got 1 plus cosine square of x to the power of 10. And now we need to take the derivative of the boundary. So we do have cosine of x, which is considered negative sine x. Well, the reason why I want to take the derivative of the boundary, because this one is considered part of the chain rule. You see that the inner function, the one that we replace here with the variable, it's cosine of x. So derivative of cosine of x, which is negative sine of x. And then derivative of 1, that's 0, so there's no need to worry about it. So we don't multiply by 0, we just multiply by the derivative of the brand new function here. Okay, so now, so this one is y prime for D. And now let's see what else that we have for the rest of this. And for E. So for E, we do have y equals integral, so e to the power of x to the power of 0, well, to the boundary 0, so sine of t to the power of 3. Or sine cubed t, or sine of t to the power of 3, dt. So again, taking the derivative both sides, so instead of rewriting it, so let me just put in d over dx like this. So we got y prime. Now, gotta be careful with this. So before you replace that the variable, so we need to flip the boundary over. Again, the rule for doing that, constant, always consider the bottom, it's considered the lower bound. And then the new function is always considered the upper bound. And then we do have sine of t to the power of 3 dt. So cancel this out. So we do have sine of, well, instead of using t, we're using e to the power of x. So sine to the power, sine of e to the power of x, and then to the power of 3. And don't forget, derivative of e to the power of x, which is e to the power of x. And that's it, y prime. Okay, so now let's go back to the slide and see what else that we have for the rest of this. So this one is part 2 of FTC. If f is continuous on the closed interval a to b, then integral from a to b f of x dx, it's capital F of b minus capital F of a. So where f is the antiderivative, that means it's the original function itself. So once you integrate it, you'll get back to the original function. And that's a function such that f prime is the same as little f. So what this one is saying that capital F is always the original function, and then f of x, the little f of x. So this one is just the derivative. So once you integrate the derivative, you'll get the original function back. So now let's do some example like this. Okay, so for a, so once you integrate that 6, so 6 is just like 6 to the 6 times x. So that's the original function. So here's another way you can check. What's the derivative of 6x? That's 6, right? So that means the integral, so you're going backward so to get the original function. So 6x. So this one is bounded from -2 to 5. And then using FTC part 2, so we do have f of 5 minus f of -2, so 6 times 5. Excuse me. So 6 times 5. And then minus 6 times -2. So basically this one is just finding the area under the curve. So 6 times 5 is 30. And then -6 times -2, which is 12. So 30 plus 12, then that'll be 42. Okay, so again, so let me just copy down the rest of the problem here so I can just show you that in the new slide. So for b, we do have integral from 0 to 1. So we do have the integrand 1 plus 1/2 u to the power of 4 minus 2 over 5. And then u to the power of 4. That one's supposed to be u to the power of 9. Excuse me. du. And then for c, we do have the integral from 1 to 8. Cube root of x dx. And then d is a trig function with the integrand, so pi to 2 pi with the integral of cosine of theta d theta. And then e, integral from 0 to pi over 4 secant theta tangent theta d theta. And then f, we do have integral from 0 to 1, and then 4 over t squared plus 1 dt. Okay, so now going back to the first one, so this one showing that it's the integral from -2 to 5, and the integrand is 6. So let me show you the graph analysis. So what this one is saying that, so let's say we do have a graph for the integral, for the integrand. Okay, let's see, we need the x-axis. Okay, so 6. So that's right up here. So the integrand is f of t equals 6. So now you only have to integrate it from 2 to, okay, let's see the boundary, -2 to 5. So you only have to integrate it from -2 to 5. So -2, -1, 1, 2, 3, 4, 5. So basically you want to find out the area from -2 here all the way to 5. So you might be wondering, wait, isn't that just the area of a rectangle? It is. So the width right here, which is what? 6. And then the length, so from -2 to 5, which is 7. So 7 times 6. Length times width, area under the curve, which is what? 7 times 6, 42. And getting back to what we just found earlier, same thing, 42. So anytime that I try to integrate it with the exact value of the lower bound, upper bound, that means you're finding the area under the curve. Okay, so now let's try the next one and see what happened. So for b, so we do have integral from 0 to 1. So integral from 0 to 1. And then it's 1 plus 1/2 u to the power of 4 minus 2 over 5 u to the power of 9 du. So taking the integral for 1, so we got u. Again, derivative of u, that's 1. Taking the integrals of 1/2 u to the power of 4, so that means we're using the power rule. But we're going backwards, so the power rule for anything like u to the power of n is considered u to the power of n plus 1 over n plus 1. Okay, so coefficient, we just want to bring it down. So u to the power of 5 over 5 minus 2/5. So u to the power of 10 at 1 with that 9, so we get a new power, and then divided by the new power. And don't forget about the boundary, it's 0 to 1. So back to the Fundamental Theorem of Calculus, part 2. So this one would be written as f of b minus f of a. So f of b, which means f of 1. So we plug in 1 to u here. So we got 1. 1/2 times 1 to the power of 5 over 5. So we got 1 over 10. Minus 2/5 times 1 over 10, which is 2 over 50. Again, we plug in 1 for u. So 1 to the power of 10, that's just 1. Multiply fraction straight across. So 2 over 50. So this one, just take care of that f of b. And then minus f of a. F of a, everything turns out to be 0. You just plug in that there. 0, the lower bound. So we got 1 plus 110 minus 2 over 50. So just reduce that a little bit. So this one we got 1 plus 110 minus 1 over 25. So common denominator, 25. So 25 over 25 plus, well, let's see. No, it's not 25. So common denominator is actually 50. Excuse me. So 50 over 50. So this one is 5 over 50 minus 2 over 50. So we got 55 minus 2, so 53 over 50. And that'll be the area under the curve of this integram. So that's for part B. And now what about for C? Okay, let's try C here. So that one shows the integral from 1 to 8. And the integrand is q root of x dx. So first thing that you want to do, let's just rewrite it for the integrand. So it's x to the power of 1/3 dx. Integrate it using the power rule. So add 1 with the power. So we got x to the power of 1 and 1/3, which is 4/3, divided by the new power. And then it's bounded from 1 to 8. So it's bounded from 1 to 8. So basically this one is just like 3/4 times a to the power of 4/3 minus 4/3. Wait, minus 1 to the power of 4/3. Again, I'm just using that f of b minus f of a right here. 4/3, once you flip it over, it turns out to be 3/4, so it's a greatest common factor. So 3/4, a to the power of 4/3, so q root of a, that's 2, 2 to the power of 4, which is 16. And this one is just 1 to the power of 4/3, which is 1. So we got 3/4 times 15. So 3 times 15, so we do have 45 over 4. So then that'd be the area under the curve from 1 to 8 of the integrand x to the power of 1/3. Okay, so now let's see what else that we have. What about for D? Okay, so for D, so this one is the integral pi to 2 pi radian cosine of theta d theta. So one thing that we notice integrals of cosine of theta is sine theta, because derivative of sine theta is cosine of theta. But we're going backward. So it's bounded from pi to 2 pi. So again, using FTC part 2, so sine of 2 pi minus sine of pi. So sine of 2 pi, which is considered 0, okay? And sine of pi, it's also 0. So that means the area under the curve is 0. So one thing you can do, it's just making the graph right here. So you can just do some graph analysis. So the integrand, it's cosine of theta, which is considered a bell curve. Okay, so check it out. So pi, so which is right here in the middle. So here's 0, here's pi, and 2 pi. And you guys might be wondering, how come the area turns out to be 0? You guys see that? This one is right above the x-axis. So anytime that you find the area under the curve, anything that's right above the x-axis, so the area of this is positive. And anything that you find under the x-axis, the area over here, it's negative. And this one, they're kind of symmetrical. It's actually exactly symmetrical. So negative, positive. So once you even things out, so there's nothing remain. So the area, the total area, it's nothing. 0. And now let's see what else that we have for the rest of this. So the next one, we do have part E and F. Okay, let's try to do that. Okay, so now for E. So we do have integral from 0 to pi over 4. So we do have secant of theta, tangent theta, d theta. For those you might be wondering, d theta, what does that stand for here? So this one is just an indicator. It's just telling you that, you know, which variable that we're using for the integral. So once you integrate this, secant and tangent, remember that, it's secant. Because derivative of secant is secant and tangent. So again, this one is bounded from 0 to pi over 4. So just rewrite it. So f of tc part 2, so secant of pi over 4 minus secant of 0. So secant of pi over 4, so secant of 45 degree. So cosine of 45 is root 2 over 2. So the reciprocals of that is 2 over root 2, which is root 2. Minus secant of 0, so secant of 0, that's 1. So the area under the curve for this integrand is root 2 minus 1. And now let's see what else for f. So this one is the integral from 0 to 1. And then the integrand, it's 4 over the quantity of t squared plus 1 times dt. Now one thing that we notice, 4 is the coefficient. We can always put it out. So we left with 1 over t squared plus 1. Okay, so back to the formula that we have for the derivative. So this one looks kind of familiar to you. So the derivative of this, what's the antiderivative of this? That's right, it's inverse of tangent. Inverse of tangent of t. So it's bounded from 0 to 1. So this one is 4 times inverse of tangent of 1 minus inverse of tangent of 0. So inverse of tangent of 1, which is considered pi over 4, and inverse of tangent of 0, which is considered 0. Okay, so simplified it. So 4 times pi over 4, so we do have pi. Okay, so that'll be the area of this rational functions from 0 to 1. It's exactly pi. Isn't that as interesting here? So pi, which is what? It's a rational number. Okay, so now let's see what else that we have for the next slide. So we got all the integrals. So anytime that you find the exact value of the area under the curve, this one is called the definite integral. Okay? So for the next section, we'll talk about some of the indefinite and definite integral. Okay, so this one is the continuation. Okay, so let's try to do G, H, and I. So now, one thing that you want to find out here, so anything that the integrand can be simplified it, so make sure that you try to simplify it first. So integral from 1 to 2. So try to separate it out. So this one is like 4 over u to the power of 3, and then plus 1 over u. Oops. My tablet is very sensitive. So u squared over u to the power of 3, so 1 over u. So this strategy is called a separation. U to the power of 3, it's just like the common denominator, so we just want to separate it. Okay, and now we want to integrate it. So once you integrate this, so this one is integrals of 4 times u to the power of negative 3. So which is considered u to the power of negative 2 over negative 2 times 4. Okay, so once you rewrite it, it's u to the power of negative 3. So add 1, so we got u to the power of negative 2 divided by the new power times the coefficient. And then what about the integrals of 1 over u? Is that going to be written as u to the power of negative 1? Add 1, we got 0. No, that's not true. So this one is the derivative of natural log of u. So natural log of u. And then from 1 to 2. So this one simplified it. We do have negative 2u to the power of negative 2. Cross cancel. So negative 2 u to the power of negative 2 plus natural log of u bounded from 1 to 2. And then f of b minus f of a. So we do have negative 2. So 2 to the power of negative 2 plus natural log of 2. So this one just takes care of f of b. Again, I'm just plugging a number to f of b. And now f of a, so minus negative 2, 1 to the power of negative 2, plus natural log of 1. So 2 to the power of negative 2, then that would be 1 4. 1 4 times negative 2, which is negative 1/2. Natural log of 2, we don't know exactly what that is. Just bring it down. Minus 1 to the power of negative 2, that's 1 times negative 2, then that would be negative 2. Natural log of 1, that's 0, so negative, negative, positive, so it's positive 2. So 2 minus 1/2, which is 1 1/2, so it's 3/2, plus natural log of 2. And that would be the area under the curve for this. Now, what about for h? Okay, so h, I want to set up the new slide for this. So h, we do have a piecewise function for the integrand. So from negative 2 to 2, f of x dx. And where f of x is split into two constant function from negative 2 all the way to 0. And the second half of this, 4 minus x squared from 0 to 2. Okay, so we're going to find out piecewise function. Okay, so new slide that we have. Okay, so for h, so we do have integral from negative 2 to 2, f of x dx, and where f of x, so this one split into 2 and 4 minus x squared, constant, linear, and quadratic. So for the constant one, the linear, so it's negative 2, bounded from negative 2 to 0. So this one shows the lower bound, upper bound for this integrand. And the other one, it's 0 to 2. Okay, so anytime that I deal with this type of function like piecewise, so that means you want to separate it. So one is bounded from negative 2 to 0. And the other one is bounded from 0 to 2. So function that we're using from negative 2 to 0, so that means we're using the constant one, so 2 dx. And then for the second piece, so we do have 4 minus x squared dx, because this one bounded from 0 to 2. So integrated, so we do have 2x, bounded from negative 2 to 0. And then the other one here, integrated, so we do have 4x, minus x to the power of 3 over 3, and bounded from 0 to 2. And using that, f of tc part 2, so f of b minus f of a, so 2 times 0, minus 2 times negative 2. So we take care of that. The first integrand. The second one, similar, so 4 times 2, minus 2 to the power of 3 over 3. So this part right here, that just consider f of b, minus f of a, so minus the quantity of 0, 4 times 0, that's 0, 0 to the power 3 over 3, that's 0, 2. Simplified it, cancel, this one's gone. Negative 2 times negative 2, positive 4, 4 plus 2, 4 times 2, 8. And then this one is negative 8 over 3 minus 8 over 3. So the rest of this is just arithmetic. It's not that difficult. So 4 plus 8, 12, minus 8 third. So common denominator, 3, so 36 over 3 minus 8 over 3, which is 28 over 3. Okay, so this one, which is the area of this piecewise integrand. Okay, so now let's see what else. So for h, and then back to the original slide here. And now what about for I? Okay, so I need more space here, so let me erase this a little bit. So now for I, it's the integral of x to the power of 3 from negative 2 to 2. So a lot of people thinking about this one, well, it's kind of like this. So you can separate it out into a piecewise function, or you can just simply integrate it directly. I mean, you can do it either way, but I do recommend you to separate it out because sometimes at certain positions, once you deal with the sharp turn, once you deal with the sharp turn of the graph, it's not considered differentiable or integrable. Okay, so let me show you the graph for this. Well, this one is fine. Okay, so it's x to the power of 3, like this. So at this position right here is still considered like a smooth curve. But if you do have an absolute value, like a V shape, then you deal with the sharp turn. And then you have to integrate it separately. But this one you can either doing it all together, or you want to separate the boundary. Okay, so how do you separate the boundary? So it's from negative 2 to 0, and then 0 to 2. So for this graph right here, which is x to the power of 3, and then for the other part of the graph here, it's 0 to 2. Okay, so dx, dx. So I just want to show you the symmetrical relationship. I mean, you can evaluate it, but once you evaluate it, eventually, guess what? The area, the total area of the integrand from negative 2 to 2 is going to be 0. Because that part of the area here, it's underneath the x-axis, so it's negative. The other part of the area, right above the x-axis, is positive. And since those two shapes right here, they're both symmetrical, so eventually they're going to cancel each other out. So 0 here. I mean, you can still go through the FTC part 2, but eventually you're going to find out it's going to be the exact same thing. So everything got canceled. So 0. Okay, so now let's see what else. So find the derivative of the function. So here's what we got for the g of x. So hint, we're going to follow through the hints. So it looks like this one I separated out from x to 0 and then 0 to 3x. The reason why that is because at a certain position here, this one would be considered as like a sharp turn, or things that's not differentiable or not integrable. Okay, so once you separate it out, so we do have integral from x to 0, so let's just rewrite it. Find the derivative, so there's no need to plug in the, well, let's just plug in the function first, f of u, okay, which is this. Okay, so we do have u squared minus 1 over u squared plus 1, so the integrand, which is what? It's a rational function, du, and then the second piece from 0 to 3x, f of u, which is u squared, minus 1 over u squared plus 1, du. Again, derivative. So that means we're taking the derivative both sides. So d over dx. Okay, so taking the derivative here, d over dx. Okay, let's see. So d over dx. So this one we're using part 1 of FTC. Now be careful with this. This one it's written as the variable to the constant power with the boundary. So we need to flip it over first. So once you flip it over, so we got 0 to x. So just switch that, the a and b value. But don't forget about the integrand. We need to change the sign so it turns out to be negative. U squared minus 1 over U squared plus 1. Okay, du. Again, I just want to flip the boundary over because normally we start with the constant lower bound with the upper bound, which is the variable. And what about this part right here? Well, this one is totally fine. It's a constant lower bound. And we do have a new functions for the upper bound, so that means we're going to use the chain rule. So this one is written as u squared minus 1. It's the same integrand. Okay, so now this one got canceled. Integral got canceled. So this one just replaced u by x. So we got negative x squared minus 1 over x squared plus 1. But don't forget, derivative of x, which is 1. Okay, so that's fine. So multiply the same thing. It's just the original rational function. But what about the second part of the derivative here? So again, this one got to be replaced with 3x. So we got 3x quantity square, which is 9x squared. Because you want to square the whole quantity. So this one is written as 9x squared minus 1. Denominator, similar, 9x squared plus 1. And it looks like we're done here, but don't forget, derivative of 3x, which is 3. So you multiply everything here by 3. And eventually, this one would be your final derivative. I mean, you can combine them by finding the least common denominator, or you can just simply keep it like this. Okay? And then the last one, so the last one is about making the graph and also doing the graph analysis from the derivative. So let g of x equals the integral from 0 to x, f of t dt, and where f is the function whose graph is shown. It's going to be on the next page. I'm going to show you that later. Well, let's go through the question first. So at what value of x do the local max and local min values of g occur? Okay, so we're going to find that out. Okay, so, and then B, where does G attains its absolute max value? And then C, on what interval is G concave downward? And then for part D, you want to sketch the graph of G. Okay, so here's the graph we do have for G of X, for f of t. Okay, so this one is just the graph of f of t. So basically we're going from derivative, and then we want to analyze this whole thing here to get all the critical conditions, like the max, min, point of inflections, concavity, and then we can figure out the graph of the original function. So now for A. So A, let's see what that is asking for. So for what value of x do the local max and the local min value occur? So back to the previous chapter, anytime if the derivative is given, so in order to find out the max, so that means we're using the first derivative test. So basically this graph, it shows you the first derivative. So since we do know that everything above the x-axis here, it's positive. So this one is positive. Positive. It's all positive. Anything right above the x-axis. And then down below the x-axis, so it's negative. Negative. So according to first derivative test, the definitions, so if the function's derivative showing that the sign changes from positive to negative, so guarantee that there's a local max. So there's one local max here. And where's the other local max from positive to negative? So it looks like it's from here at this position. So that means at 2 and then 6, so we do have the local max. Okay? So at the x value of 2 and what else? 6. Because that the first derivative, it changed the sign from positive to negative. So guarantee that we do have 2 local max. Okay, so that takes care of the first question. And now let's go back. So where does G obtains its absolute max value? Absolute max. So absolute max, that means we need to test the endpoint. We need to test the to find the area under the curve. So let's just compare the area under the curve right here. So from 0 to 2, what do you notice? Well, obviously the area from 0 to 2, it's a whole lot bigger than the area from 4 to 6. So that means at 2, it guaranteed that it's an absolute max. So this one, it's not just the local max, but also guaranteed that's the absolute max. For those of you who might be wondering, what about the endpoint? Well, the endpoint, this one, you try to compare that, the area over here, it's not as big as the previous area under the curve, so we don't count that. Okay? And now let's see what else. Okay, it's absolute max at 2. Okay, so now for the next one. And what interval? It's G concave downward. Okay, so this one is a little bit interesting. Concave downward, so that means we need to find out the concavity. Again, keep that in mind. The graph is given as the first derivative. In order to find out the other derivative, so that means you want to find out the increasing, decreasing interval. So if that's concave downward, so that means the derivative will be considered negative. As you can see that the graph from 1 to 3 here, what happened for the curve? It's all decreasing. And then from 5 to 7, what happened with the curve? It's also decreasing. And then from 9 to 10, it's also decreasing. So for the concave downward interval, so we do have from 1 to 3. Again, this one is the interval. Union, what else? This one right here, from 5 to 7. Again, this one is the first derivative. Concavity would be the second derivative. So you take the second derivative, so that means the graph got to be decreasing. Okay, so from 5 to 7. And then union, 9 to 10. So for those interval, you'll find out the graph, the original function, is going to be considered concave downward. So by the time that we sketch the graph, you'll see this, okay? So now the last part of this, how do we sketch the graph of the original functions? So the first derivative is given. How do we find the graph for the original function? How do we sketch it? Okay, so now it's all about what we've been doing, finding the area under the curve. If you try to approximate the area of the curve from 0 to 2 here, well, let's count the grid. So each grid is representing 10, because that the y scale is by 10. So 10 times 1, then that's 10. So 10, 20. This one is about 30, 40. Okay, so this one over here, I would say, well, it's almost considered another 20, but it's a little bit less. Okay, so again, this one right here, 10, 10, 10, 10. So then that's 40. So this one is almost another 20, but it's kind of like getting close to 17. So then that'll be 47. So 47 up here, that's about 10, I would say. 57. So this one is a little bit less. Okay, so 40. 57. 67. And this one is about 5. So 67 plus 5, which is 72. Okay, count it one more time. So each grid right here, it's considered 10. So 10, 20, 30, 40. This one, 2 together, combine it together is 17. So it's 57. 57 plus 10, 67 plus 5. So 67 plus 5, 72. Okay, so the area from 0 to 2, so it's about 72. So let's set up the scale. So this one is going up by 10. Okay, so 10, 20, 40, 60, and then 70. Okay, let's just set up the scale. 20, 40, 60, and then this one's 70, 72. It's right here. Okay. And now, what about the area from 2 to 4? From 2 to 4, again, this one is negative, so that means it's going to be down here. Got to be careful. So each unit, it's by 10. So 10. This one's about 17. No, it's 7. So negative 17 altogether. So this one, it's about negative 8. So negative 25 over here. Probably about another negative 8. Negative 33. Over here, that's about negative 5. So negative 38. You know what? Let's just reset the scale. So this one, we're running out of space down the bottom. So instead of using 20 for the Y scale, so let's use 30. So 72, most likely, it's about over here. So this one's negative 38. So that's going to be down here somewhere. Okay, so now what about the area from 4 to 6? So the area from 4 to 6. Okay, let's count this. So 10. This one is about probably 8, 5. So we got 18, 5, 23, another 3. So 26. Okay, so 26. Somewhere right there. Okay, making sure that this one going to be matching. So this one, 26. It's supposed to be right here. Again, this one is the area from 4 to 6. And now, what about the area from 6 to 8? Negative again, so it looks like this one, negative 8. Another, well, this one looks like it's almost another negative 8. Negative 7, so negative 15. So at A here, so it's negative 15. Right there. And then, what about the area from 8 to 10? So here's about 8, 9, so 17. So 17, so 15, 17. Okay, make sure that this one's going to be lining up like that. Okay, so now what do you notice? So once we get the point, so basically we can just connect this all together. As you can see that the derivative right here, so this one it's increasing, so that means, so for this part of the graph is going to be considered concave upward. Okay, so see that this one, if you try to find a derivative, it's positive. Okay, so derivative is positive, so that means the concavity, which is concave upward. So concave up. And then over here, it's going to be concave down. So this one, it shows the point of inflections at 1. Okay, like this. And then it's going down. And also this one right here at 3, it shows the point of inflections. Okay, you see that right here? Negative, so it's concave downward. All the way to 3. And then from 3 all the way to 5, it's increasing, so that means it's concave upward again. So 3 to 5 is concave upward again. Oops. So you got to be a little bit careful with all the element here. First derivative, concavity. Okay, again, at 5, that's just another point of inflections. Okay, so the one that I have right here, point of inflection. And then over here it's concave downward, so this one is downward all the way to 7. And then from 7 to 9, concave upward again. So 7, 8, 9, concave upward. And then all of a sudden, right here, 9 to 10, concave downward. that. Okay, so then that would be the function of g of x. So again, anytime that you find this, make sure that you need to find the max first. So again, at 2, we do have a local max. Not just the local max, but also shows that it's the absolute max. And then another local max we do have right here at 6. And also you can say that there's another one which is at what, 9. But also don't forget about the local min. So local min, if you see the sign change from negative to positive for the first derivative, then you'll find the local min. So the first local min, it's right here at 4. Okay, and here's another local min. Okay, so change the sign from negative to positive. So that's right here at 8. Okay, and then all the vertices right here, the max, the min for the first derivative, it shows the point of inflection. So at 1, we do have the first point of inflection. And then at 3, we do have another point of inflections. And then here's another max for the first derivative. It shows another point of inflections, which is at 5. Okay, right here. And then 7, another point of inflections. And also at 9, another point of inflections. Okay? So make sure that you guys watch this video precisely. So gotta be careful watching it. And also always watch that a couple times. So there's so many information. There's so many detail involved. If you miss one thing, it's very difficult to figure out the next step. Okay? So watch that over and over again. And let me know any questions that you have. Okay? So thank you for watching the video today. And make sure that I try to do some of the homework problem regarding sections 5.3. Okay, so I'll see you guys next time.